So we started with pointers, and we had a simple introduction to dynamic arrays, but today we're going to continue with the details of dynamic arrays. And we started with dynamic memory allocation, so we looked at an example similar to this. And now we know that the new operator does two things. The first thing is that it will create an unnamed variable, and the second thing is that it will return the address of this unnamed variable to the variable p. And we mentioned that all such dynamic variables, they're stored inside special location inside the memory, which is called the heap or the free store. Now this is a simple example, but it has a couple of new syntax elements that we have to become familiar with. The first syntax element is the command type def. Type def stands for type definition. And this is just cosmetics. This is saying, this is informing C++ compiler that whenever you see this identifier, which is the integer pointer, just replace it with *int. So the C++ compiler, whenever it sees the int pointer, it will just replace it with a star to an integer. So it's just cosmetic. It has no functionality. Okay? Some people, they say that the purpose of this is to make the program a bit more readable. And you can agree or disagree, it's up to you. But at least you have to be aware of it. So this is called the type definition command. So let's see what we have in this example. In this example, we have a function which is called sneaky. And it receives one variable which is called temp. And the type of it is an address of an integer, right? Okay. And we're creating an integer, unnamed integer. We're assigning it the value 77, so we're storing 77 inside the content. And then we're printing out the value of it, so what will be printed out at this point? 77 clearly. Then we're passing it to a function. Now this is the function, it's receiving the pointer. The function, it received the address, right? So the TMP, it's the address. The P itself is the address. Star P is the content. So star P is 77. But P is the address, right? The analogy we looked at last time, we said that star P is the content of the locker, and P is the key, right? Okay. So what we are passing to the function over here, we're passing the key. So now the function, using this key, it can access the locker, it can dereference the content, and it changed the content from 77 to 99, okay? Now when it prints out inside the function over here, obviously it will print out 99. Now the function is done, so we go back to main and we print out P, and P, now the content in P is also 99. Okay? Because what this function did, it opened the locker using the key, it removed the 77 and it replaced it with 99. Fine? So we went back to main. When we use the same key, when we open the locker, we don't find 77 anymore, we find 99. And we started with dynamic arrays. And we mentioned that, as you know, this is a static array, the size is 10, but this is a pointer in which we can create an array. And the command for creating the array that we have looked at, it looks like this. So what we have over here, we have a double pointer, which is just a star to double. And we say that d is equal to new double 10. And we looked at this last time. Briefly, what it says is, we're not interested in creating one double, but we're interested in creating 10 of them. Okay, so it's 10 continuous doubles. So when you have 10 continuous integers or 10 continuous doubles, obviously this is an array. The type is not restricted to integer or to double. We can use character as well. So you can use any type, float, integer, character, double, any type that you have. So this will create an array, and it will return, and we know that the new operation or operator, it will create the unnamed variable and it will return the address. But over here, how many doubles did we create? But which address will be returned to D? The first one, yes. Okay. So the address of the first double will be returned to D. Now, previously we mentioned the following. Maybe you remember it, maybe not, but this is the time to repeat it. We mentioned that the name of the array actually holds the address of the first element. Do you remember that? You don't? Let's repeat it. The name of the array in C++, whether it's a static array or a dynamic array, the name of the array is actually contains the address of the first element inside the array. So now this array contains 10 integers, right? And A holds the address of the first integer. Now, believe it or not, internally, this A, it's a pointer. Although it's a static array, but this A is a pointer. This pointer A is different than this pointer P because this pointer A, it's a constant pointer, which means that we cannot change the value of A. We cannot change the address. The address is the key. We cannot change the key. The key will remain as is. Now this pointer, it's a free pointer, which is P. So you can change it. So you can say P++. You can say P minus minus. Okay? But A, in static arrays, it is a pointer because it holds the address of the first element inside the array, yet it's a constant pointer. So you cannot say A++ or A minus minus. Okay? Now, as a consequence of this, we can take P. P is an address of an integer, right? And A is also an address of an integer. So there is no harm whatsoever to say that P is equal to A, because both of them, they hold addresses of integers. So there is no type mismatch at this point. We took an address of an integer and we stored it inside P. Now, both P and A, they have the address of the first element inside the array. So now you can think of a one-dimensional array being pointed at by A and by P, which means that you can now manipulate the content of the array through either A or P, because both of them are referring to the address of the array. Now, however, the other way around is illegal. P, it's an address of an integer. A is an address of an integer as well. So there is no type mismatch. However, this A, it's a constant pointer, as we agreed. So if it's a constant pointer, you cannot change the value. Right? So by definition, guys, a static array in C or C++, the name of the array holds the address of the first element. So it's a pointer, but it's a constant pointer. You cannot change the value of the address. But why is this important? We'll look at examples in a minute. So we can see in a minute that you can create an array, have a pointer pointing to it, and then manipulate the content of the array through the additional pointer instead of the original pointer. So we'll have a play with this in a minute. So the array variables, and this is the title, the array variables, it's actually a pointer. Now this will start to give us an understanding that when you pass an array to a function, it behaves like call by reference. Do you remember that? Because you're actually passing the address. And if you're passing the address, then you can have access to the contents, right? So that's the trick. So this is how it looks like. It's actually a constant integer star. So it's the address of an integer, but this address is a const. You cannot change it. You cannot say A++, you cannot say A is equal to P, you cannot say A minus minus. And dynamic arrays, we know why we need dynamic arrays. Obviously, we discussed this before. You want to create an array, but you don't know what the size of the array is. So the best way is to run the program, ask the user for the size, and then run the program. Otherwise, you might end up with wasting memory because you're going to create a very large array and the user is going to use it partially. Do you remember partially filled arrays? Or otherwise, you might create an array and it's too small for the user to enter the information. Okay, so static arrays, they have their limitations, as you know. Okay, so that's why we resort to dynamic arrays, and this is the definition of it. Just simply, instead of using this, then over here it can be integer size, cn size, and then create the array. Okay. Now, once we are done with using the array, last time we looked at the command which is called delete d, but now in terms of syntax in C++, this informs C++ that, look, I'm not deleting a scalar, but I'm deleting an array. I'm deleting a list of scalars. So as opposed to delete d, there is delete array d. Okay? It will take you time to get used to the syntax because you might think that an intuitive way to write it is this, delete d, right? But the syntax doesn't look like this. So we have two options. If d was a scalar, this is what you do. And if D was an array, then this is what you do. طيب. Of course, you have the book next to you. You can always refer back to the syntax. Once you do it a couple of times, you'll get used to it. Okay. So the brackets, they indicate that what we're deleting is actually an array. طيب. Now, having deleted the array, now we know that the content will be deleted, but not the key. Do you remember? And the key, if we keep the key and we try to access the content using the same key, the problem is called the dangling pointer. We talked about this last time. I hope that you studied the last time lectures. So to get rid of this problem, simply after deleting D, we just set D to null. So this is the same arrangement as we did before. Nothing new over here. Okay. We'll look at examples in a minute, but let's finish a couple of slides. We know that you can pass an array to a function, and we also know that the function cannot retain an array, right? So there is no such function declaration in C++. When you do Java later on, you'll see that you can retain an array from a function in Java, but not in C and C++. Fine, we cannot retain an array, but fair enough, we can retain the address of an array. We can retain integer star. This integer star, it might be a pointer to one element, or it might be a pointer to an array of elements. So now we can retain an array. You're not actually retaining the whole array, but you're retaining the address of the array, which will suffice. Okay. Okay. One last slide, I guess, before the examples. Now we created an array, and the name of the array was D, right? This was the double array in the previous slide. So we created an array. Here we go. So we created an array called D, and it's an array of 10 elements. All of them are double. Okay, now the last topic that we have is pointer arithmetic. And in pointer arithmetic, it means that what are the arithmetic operations allowed in pointers? Okay, not all arithmetic operators are allowed in pointers, and the ones that are allowed, they behave differently than regular arithmetic. So this is what we need to understand now. A very simple topic. So now we have D, and D is it holds the address of the first element inside the array. Now, if you say D plus 1, now how many bytes do we have inside the double? 6 bytes? 8 bytes? Whatever it is. And we know that the array is a sequence of bytes, right? And each byte has its own unique address. When you say D plus 1, the first thing that should come to your mind is the next byte, right? And if you say, because it's an address, and each byte inside the memory has its own unique address. So when you say D plus 1, it's the next byte, and D plus 2, it's the next byte after that, and so forth. However, in pointer arithmetic, it has a different interpretation. It has a different meaning. When you say pointer plus 1, it means point to the next double. Now the next double might be 6 bytes away, it might be 8 bytes away, it doesn't make a difference. So if D holds the address of the first element, then D plus 1 holds the address of the second element, regardless how many bytes are they apart. And D plus 2 holds the address of the third element, and so forth. If this was an array of character, the size of the character is a byte, right? So when you say D plus 1, you're actually moving to the second byte. If this is an array of integers, when you say D plus 1, you're moving 4 bytes ahead, because the size of the integer is 4 bytes. So in pointer arithmetic, when you say plus 1 plus 2, or when you say D plus plus or D minus minus, what you're actually doing, you're either moving to the next element or to the previous element, regardless how many bytes apart the next element or the previous element is. Okay, so now this means the following. We're going to step through the array using what's known as a pointer notation, as opposed to a array an array notation. This is the array notation, we're used to it, right? But this is called a pointer notation. So this is an array notation, and this is a pointer notation. Now, if we want to loop through the array and we print out the elements of the array, this is what we do. Of course, this has to be an I, right? Not an L. So this is lowercase. Now, we mentioned last time, so okay to repeat it, that once we create a dynamic array using a new double and then array brackets 10 or whatever have you, you can deal with D as if you're dealing with any regular array. So if you want to print out the content of the array that you have dynamically created, you just simply use a loop as if you're dealing with a regular array. So this is the array notation. However, we can also rewrite this using a pointer notation. So let's understand this pointer notation. Now we agreed that the star, it means dereference, right? Okay. Now the first value of I is 0. So we are dereferencing D plus 0. D plus 0 holds the address of the first element, right? Now in the second loop iteration, we are dereferencing D plus 1, which is the second item inside the array, and then D plus 2, which is the third item inside the array, and so forth. Now believe it or not, guys, in C++ behind the scenes, when we write such code, C++ will convert it to this code. Okay? So it will actually dereference plus an offset. This offset is the array index. So now in the lab, specifically, we're going to give you a question and say, solve the question using an array notation, and then solve the problem using a pointer notation. Okay, so we have to be familiar with both of them. But at the end of this loop, to which element will D be pointing at? Array size minus 1. What else? Array size. What's the array size? Array size. What else? At the end of this loop, to which item will D be pointing at? The last item of the array. What else? Yes, the last item. What else? Going once, going twice, gone. The first one. Did you see anywhere inside this code that we said D is equal to D plus 1? Did we change the value of D? We did not, right? Did we say D plus plus? We did not. We did not change the value of D. So where is D pointing to? The first element, right? So by the end of this loop, D is still pointing to the first element. By the end of this loop, where is D pointing to? Yeah, still the first element, right? We did not change the value of it. But now, had we used plus plus and minus minus, it would have been a different story, because we can write this code using this approach. So next to it, I'm going to write cout. I'm going to dereference D. Is this correct? We have to check this. Dereference D. We have to check. Yeah, we'll have to check. Do we need the brackets or not? We'll try it in a minute. So what happened? We'll double check in a minute. But what this means, guys, is that we are going to dereference D and print out the content, and then increment d by 1. Incrementing d by 1, it means point to the next element. It might be 4 bytes away, right? So now at the end of this array, at the end of this loop, where will d be pointing at? If you write it this way. The second one? Wrong. Last one, wrong. Second last? What do you mean? Do you mean the one after the last? One before is wrong. In fact, it will be one after, right? Because we are dereferencing and then we're incrementing the address, right? So we're going to print out the last item and then increment. So we're going to be pointing outside the array. This is dangerous. If you use this, you have to use it very carefully, because D is no longer pointing towards the first element. Now it's pointing outside the array. So if you try to access the content, you're accessing the content outside the array. Now just to let you know, C and C++, they're considered to be unsafe programming languages because of this, because pointers can be used to access the memory at any content, at any address. Usually hackers, when they write viruses, they use C and C++ because they can access the content of the memory. Other programming languages, they don't have such features like Java, so Java is much more safer than C++. So C and C++ is unsafe because of the pointers, yet it's much more flexible. So it's flexibility at the cost of safety. So anyway, we'll try this in a minute. So what we did last time, we created an array, dynamic array. We can use the same code. So we ask the user to enter the content, to enter the size, and then now we have a new array which is called ARR, right? It's a dynamic array. Let's also have another pointer. So we have an array which is a pointer, and we have star p also. So we have two pointers. P does not have a value yet, right? So what do you think happened now? What's the result of this statement? The address of the array is stored inside P. So now we have P and ARR pointing to the same content, right? Okay. So now we can access the array through P. So we can say that for integer I is equal to 0, I is less than size, which was entered by the user, and I plus plus. And over here we can just cn P of I. We can use an array notation to do so, right? So we're dealing with it as if it's a regular array. We could have also written, and it's exactly the same meaning, ARR I, because now we have one array with two names. Okay? In C++, they refer to P as an alias. So now we have an array that has an alias, an additional name, which is called P. Okay? So, fine. Then let's print out the array. So for integer I is equal to 0 and I is less than the size and I plus plus. Now let's do it this way. So we're going to see out. Let's see if this works. And line. Now we're going to debug the code and see how is it that P is being incremented, and we're going to see how is it pointing outside the array once we are done. So we can have a breakpoint over here. Start debugging. Array size 3, content 1, 2, 3. Okay. A couple of things before we start. Look at A and P. Do they have the same address? Because both of them are referring to the same array. And surprise, both of them, well, it's not a surprise. Both of them, the type of them are address of an integer, right? Now if you expand them, you will see that they're referring to the same content. If you want to see the actual content, you can go to watch, and you can do the following trick. So you can say what's stored inside this location, what's stored inside this location, what's stored inside this location, what's stored inside P3. No, it's not a string. It's not a string. P3 is outside the array, right? We don't know what's stored inside there. This is something that was inside the memory. We don't know. Okay. What's stored inside star P? It didn't like it. But maybe this doesn't work in watch. But we can use watch with array notation. Did I write it as a capital P? Right, I did. So it was a typo. So if we have star P plus 1 and star P plus 2, right? So P0, P1, P2 are exactly this notation. So this is the pointer notation, and that's the array notation. Okay, so let's go back to bugging. So I'm going to click on local variables. Okay, so let's print out one element. Okay. What happened to P? Now it printed out 1. So we entered 1, 2, 3. Now it printed out what? But what happened to P, guys? The address moved to the next element, right? Because we said P++. Okay, now continue. It should have printed out 2 over here. So you can say CD2. And the address is moved ahead. That will print out 3, and the address moved ahead. And then it's done, right? But now if you go to watch, and I'm going to ask what's inside P. What's inside P at this point? Garbage, we don't know, because we already exceeded the array boundary. Because after the last element we said address plus plus. So now P points outside the array. We printed the last item and we moved outside the array. So now P is pointing outside the array. So we don't know what's the content inside the array. This is the number that was there inside the memory. Okay, so this is called pointer arithmetic. We can do P++. We can also do P plus 1, P plus 2. We can say P is equal to P plus 1, P is equal to P minus 1. We can traverse the array in reverse order if you use P minus minus if you wish. Now, I'll answer your question in a minute. Now, one very typical common mistake, guys, over here is to try to access P after moving it. So if you try just simply to say P of I, if you look at this code in isolation, it's very innocent, right? P holds the address of the first element, and I'm just printing out the array content. If you look at this piece segment, code segment in isolation, it's very innocent. It's not doing anything wrong. However, if you look at the context of it, if you look at the previous code, you understand that P now points outside the array, right? So now you're printing 3 elements from outside the array. Your program might crash, your program might not crash. Most likely it might not crash. Start without debugging. So 3 elements, 1, 2, the first one was the size. Start without debugging. The size is 3, and then 1, 2, 3. It printed out 1, 2, 3, which is the first loop, and then the second loop, which looked innocent. It's not at all innocent because you're printing out numbers from outside the array boundary. So it printed out 1, 2, and 3. Okay, this is a very common mistake if you're using pointers, guys. Very common mistake. The fact that it's not a syntax error, the fact that the program does not crash, it will take you forever to debug such code. If you're writing a small program, doesn't make a difference. Okay, but if you're dealing with real programs where you have 70 files in your project, then it's a different story. Okay. But at this point, if we want to put P back to the first element inside the array, what can we do? Say again. P is equal to P minus 3. Would that work? Now P is pointing at 4, right? So when you say minus 3, 1, 2, 3, that would work, right? Would it work if you say P is equal to P minus size? Let's try this. Start without debugging, 3 elements. 1, 2, 3. It's working correctly, right? So now we moved P, this is the array, and we moved it outside the array boundaries, right? And then we said P is equal to P minus 3, so we moved 1, 2, 3. Now P is back to the first, pointing back to the first element. Is there another way to do it? So this is one way to do it. How else can we do it? Yes, exactly, yes. Because ARR did not move, right? So when we say A is equal to ARR, now both of them are pointing to the first element inside the array. Right. What we could have also done is, we don't have a problem in this case, right? Because we did not change P. Do you agree? Not plus 1, plus I. Not plus 1, plus I, of course. Right. In this case, we did not change the value of P. Right. And one last thing to do, which was in the slides, function that returns a pointer, right? So creating an array, we can create the array inside the function now instead of doing it over here, just for the sake of illustration. So let's have a function called allocate array, and we're going to pass it ARR. Pass it the size, or we read the size in the function. We can read the size in the function. No, but we need the size in main. So let's pass it the size. Well, I think it can be done in 2 ways. It can be done with retaining a value or without retaining a value. Let's see. طيب, help me out. Let's declare this function now. The type of size is, this is straightforward. What's the type of ARR? Integer star, right? And what's return value? Also integer star, okay. طيب, let's define the function over here. So it's not doing much, just simply saying that ARR is equal to the new int of size, and we're just simply returning ARR. So what we're returning is an address, right? ARR, it's an address. We're returning an address, and the return type of the function is also an address, so there is no type mismatch. There would have been a type mismatch if we do this. Now this is a syntax error, because the type of ARR is integer star, and what we're returning is an integer. It doesn't work this way. So this has to be an integer star. And C++ should be okay with it. Type. So now we're returning this integer star, and we're storing it inside ARR. ARR now will contain the address of the first element inside the array, which was created inside the function. Now we mentioned previously that whenever you create a dynamic variable, it goes inside the heap, and it will remain inside the heap until we explicitly delete it. Do you remember? So don't think, now many people, they would say, that since this array, or would think that since this array was created inside this function, so the array only lives between those two curly brackets. That's not the case. Now we mentioned previously that if you have any variable created within U, it will remain there inside the memory until you explicitly delete it. Fine? So now we returned ARR. What we have actually returned, we did not return an array, because C++ does not allow us to return an array, but the way around it is to return the address of the array. We created an array, we returned its address, and we stored it inside ARR over here. Okay. But we do not need to pass ARR. And what we can do over here is to have integer star. I'm going to give it a different name now. My. Do you think this will work? This is even more reasonable. Okay. And now, so we call the function. We only pass it the size. We say, look, the size that we are interested in is 10, 20, or whatever it is. And now what this function will do, it will just create a new array inside a local variable called myRR, and it will return myRR. When it's returning myRR, it's returning the address of the array that was just created, right? Once we exit from this function, the local variable myRR will disappear, but the unnamed array will remain there. And what we have actually returned is the address of the unnamed array. And this is where we have returned it. So we return the address, and this address is now stored inside ARR. Very quickly, let's debug this to translate what I have said, which seems to be Chinese to some of you. Start debugging. So the size of the array is 3. And now this is the function. Let's step inside the function. The size is 3. We created a new variable which is called myRR, and this is the address, right? So this is the address of the unnamed array inside the heap. Fine. Now what we are going to do, we're going to return this address. Look at the number, it ends up with 28, right? The address, it ends up with 28. We return back to the caller. ARR at this point does not have a value yet, it's not assigned. But once I move one step ahead now, the address which ends up with 28 will be stored inside ARR. So the ARR is supposed to hold the address of the first element inside the array. So let's do that, and here you go. ARR ends with 28, which is the address of the first element inside the array which was created inside the function. Okay, and now the rest of the program will work perfectly well. So what we have illustrated in this example is that we can return the address of an array from a function. And typically this is used in creating arrays. Of course you can use it for other purposes as well. But there is one thing missing in this program. What is it? Delete. Thank you. So the last thing that we have to do over here is to delete. Now we created an array which is inside the heap, but we did not delete it. How do we delete it? Delete, and then brackets, and then one student said, Abdulmaz said myRR, and we have to give you a big X for that. Now myRR, guys, it was a local variable inside those two curly brackets that no longer exist. It's a local variable and it vanished, it's no longer there. But what's there is the unnamed array. So myRR is incorrect. What else? What do you suggest? ARR. Do you think this will work? But how about delete? Do you think this will work? But why not?
Well, if we delete every flower square, the new item.
We have one array, right? How many names does it have? What are they? A, we can delete it quickly, and we can delete it for it. There's no harm in doing so. Yes. But now at the end, after doing this, we have to say, to make sure that we don't have the dangling pointer problem. Now, another common mistake that people working with, or programmers working with pointers might fall into, is the following. We have deleted the array, right? And somewhere else inside your code, you don't know that P is referring to an array which was deallocated, and you're just trying to access the content of that array at this point. So let's take this out. Again, this is a very common mistake. So you deleted the array using one name, but you're trying to access the array using the alias, the second name. Now the array is no longer there, right? It was deallocated. So what do you think will happen when we try to print out over here? It will print out garbage, right? Because the array was deallocated. Let's compile and run. So 3 elements, 1, 2, 3. So the first time it was printed out correctly. The second time we printed it out after deallocating the array. So you deallocate the array, you cannot access it through the alias, through the second name. Again, this is one very common mistake. Okay, so P is also equal to null. By doing so, we make sure that both names of the array are no longer accessible. Okay, we cannot access the content through those two because the address is set to null now. Any questions? Yes. At this point, the last two rows. Ask again. I think I got your question, and let me answer you with this. Size of the array is 3, 1, 2, 3. Now, we have two names, ARR and P, right? Still, we did not assign them to null. Can you see it? Okay, now let's assign one of them to null. P is unaffected. Was this your question? You thought by assigning ARR to null, P will also be affected? This is what you thought, right? Now, when we say ARR, we're not talking about the content, we're talking about the key, the address. So you have actually changed the address that is stored inside ARR to null. But now, when you explicitly say that P is equal to null, now both of them they're equal to null. Okay. Now, to further address your question, it would have been a different story if you come and say that ARR is equal to 10. Now, what happened at this point is that you've changed the first element from 1 to 10 because you dereferenced, right? So now the first element is changed to 10, and this change can be viewed by ARR and by P. If you change the content is accessible by ARR and P. But if you change the address in ARR, it does not affect P and vice versa. Okay guys, so we have to stop here.